the last couple of lectures we have been looking at the wave properties of light, and so we have defined the concept of phase of a light wave, and then based on the phase of the light wave we have said okay, light waves go through interference phenomena, and through that by looking at constructive and destructive interference, we have been looking at how light tends to be brighter at certain spots and not so bright at other spots. So, we took the example of Young's double slit experiment, and then we extended to multiple slits, and then we came to the conclusion that when you go for multiple slits, more number of interfering sources, you have more constrained interference criteria, which provides you much better selectivity in the response. And so, we had taken the specific example of wavelength selectivity, but in general phi is given by 2 pi over lambda d sin theta. So, even for a constant wavelength, you can say that spatially when you look at the interference pattern, spatially the interference pattern is going to be much more sharper when you consider multiple sources of interference. And we are going to be looking at some examples. Of course, we looked at an example of a compact disc in the last lecture. So, we said okay, the CD has multiple grooves which essentially provide you this interference criteria. So, you can separate out colors, and that actually is a subset of a larger class of components called diffractive components. So, just the principles that we have looked here in terms of multiple slits can be extended to having optical components which are called diffractive components, diffractive optics, which essentially allow you to change the characteristics of light. How? So, if light is going in a particular direction, it allows you to bend light or direct light in a particular at a particular direction. Okay. And of course, when we look at this interference criteria, what this tells you is that okay, you can direct light into multiple orders, right. The 0th order would correspond to the same direction that the incident light had, but then first order, second order, third order and so on is going to have different directions defined by this theta, right. So, different orders are going to have different directions, right. Or you could do some manipulation with the phase at the point of the slit, okay. And you will have specific examples of that as part of the tutorials, where you could direct light into a particular order. Okay. So, this is a general criteria where we say okay, it is the incident light which has a very specific direction is actually diffracted into multiple orders, but you could also come up with manipulations at the point of the slits through which you can direct most of your light in a particular direction, and that is similar to the concept that you might have encountered in antennas. You have something called phased array antennas, right. Have you heard of that, phased array antennas? So, by manipulating the phase and the amplitude with each of those sub antennas, you can actually have a very specific radiation pattern. In fact, you have a radiation pattern that can scan across different directions just by manipulating the phase, the relative phase between the different antenna elements. So, similar concepts can be possible here as well. You understand that? So, you could direct most of your energy in a particular direction, and it's a slightly more advanced concept. We don't have time to go into that, but we'll try to give you a sample of that through the tutorials. You'll work out one problem in that. Okay. So, this specific configuration of this multiple slits, but we can easily see that similar principles can be extended to when you consider something like this Fabry-Perot. Sorry, I meant to just highlight this, right. So, when you consider Fabry-Perot, you are essentially having multiple reflections, and all these different reflected components are essentially going to constructively interfere at this particular point, which allows light to go through. So, you could potentially extend this concept of multiple interference to this Fabry-Perot case as well. Only difference will be that in a case of a Fabry-Perot, you would have a certain reflectivity for the mirrors. So, the reflectivity in terms of power, and if you want to look at it in terms of the amplitude, it will be root of r for each of the mirrors. So, the reflected components essentially are going to have lesser and lesser amplitude. Okay. So, all the interfering components are going to have lesser and lesser amplitude, and that is different from the case that we were looking at. I thought there was, yeah, okay. The case that we were looking at over here, so when we were talking about a phasor diagram, we said in this multislit case, you have equal intensity for each of these phasors, right, equal amplitude for each of these phasors. But if you have a configuration like a Fabry-Perot, where you have a reflectivity, okay, which is less than 100%, each time it goes through a bounce, it is going to lose some of the light, right. So, the phasors are not going to be equal, they are going to be diminishing in terms of their amplitude. So, correspondingly you have a slightly different result, but nevertheless most of the other principles in terms of the number of interfering sources, defining the interference criteria, the constraint in the interference criteria, all those things would carry on. Okay. So, let us move on from here. Let us actually towards the end of the last lecture, we were looking at this Michelson interferometer, okay, and the Michelson interferometer is essentially this configuration over here, and we said you could basically split it into two arms, and in the two arms you put a mirror and deflect it back, and if you are observing the interference output, that output would depend on the relative phase that the light waves in the two arms have accumulated, and then you come up with this criteria that the path length difference, if it is m lambda over 2, it corresponds to constructive interference. Now, some of you are wondering where is this factor of 2 come into the picture, right, because in the multislit case we said the path length difference has to be equal to m lambda, and here we are saying m lambda by 2. Where does the factor of 2 come from? The fact that it is taking a bounce, it is taking a round trip. Now, of course, if you can choose to represent the path length difference as 2 into d1 minus d2, in which case it is m lambda. Okay. So, there is no magic about this factor of 2 here. Okay. So, what we want to do is we want to extend this concept of Michelson interferometer to introduce one more concept, okay, and that concept is coherence of light. Okay. So, to give you a idea of what coherence is all about, so far in all our examples we have made two assumptions, okay, or at least in the case of a Michelson, one of those assumptions was that we have monochromatic light, because we have been looking at all these interference conditions with respect to only one wavelength, right. So, this is actually for a monochromatic wave. And when we were talking about double slit, we said you have a plane wave that is incident on this double slit, okay. Guess what, in reality there is no such thing as a perfect monochromatic source, there is no such thing as a perfect plane wave source, okay. You have something that is very close to that, but not exactly that, okay. In reality these are polychromatic, and these also have these are not absolutely planar wave fronts, these light waves. So, what is the effect of that on the interference, and how do you quantify that? That quantification, what we are going to see is through this coherence, what we call as either temporal coherence or spatial coherence. So, let us go ahead and try to define all these terms. So, let us start with looking at the coherence property of light. And I should give a disclaimer here. This coherence property of light, which actually leads you towards the quantum optical principles of light, is a fairly deep subject, okay. And what we are doing here as far as this course is concerned is just giving you, we are just skimming through that topic just to give you a basic feel for what this is all about. And of course, if you are interested, you can go into a deeper reading of this topic, okay. There is much more available there. So, let us actually look at this. Let us take this example of a Michelson once again. We have a beam splitter here which splits light, let us say in two ways, okay. So, you have a light beam coming in that is getting split, and you put a mirror over here and a mirror over here, bounce it back, this also bounce back, and then we are observing over here, okay. Now, we have not actually defined many of these optical components. A mirror, you can say, corresponds to a metal coated substrate, okay. So, that can act like a mirror, but there is also something called dielectric mirrors, and similarly with a beam splitter also, if you want to achieve a perfect 50-50 split, what you use is what is called a dielectric coated mirror, okay. And there again, some of the principles that we have talked about in terms of handling phase, okay, is going to come into the picture. So, you are going to track phase as it goes through multiple layers. So, at any one of these interfaces, so I am actually deviating from this topic a little bit, but all these dielectric mirrors will have two material, NH and NL. So, let us say NH corresponds to a high refractive index material and NL corresponds to a low refractive index material. And if you have alternating layers of that, and then if you have a wave that is incident on it, it is going to go through reflections at each of those interfaces where the refractive index is different, right. So, that is what you call as Fresnel reflection, and all these components that are reflected, if they are all in phase, they will all add up together, and you will get perfect reflection. All the light that is going forward, it is all going to get reflected. Or you could have a lesser number of layers through which you do not reflect all of the light, you reflect part of the light, let us say 50% of the light, and then the other 50% is going over here. That will be a partially reflecting mirror. Okay. So, you can make mirrors using some of the principles that we talked about so far. What you have to do is essentially look at what is the relative phase of all these components that are getting reflected from the different interfaces. Okay. Of course, this and we will have a tutorial problem on this concept as well, so you can appreciate some of the details of this, but you could go to the extent of connecting to Bragg diffraction theory. You all have in high school learnt about Bragg diffraction, right? So, if you have a periodic arrangement of atoms, if you come in with a X-ray radiation, then you have these X-rays diffracted and they all constructively interfere in a particular direction, right. Through that you can possibly tell what is the period of this atomic spacing, right. So, that principle is not very different from what we are learning here about multiple slit interferometry, or in this case multiple layer interference. Okay. So, you can say that this multiple layer interference is actually a one dimensional Bragg reflector in that sense. Okay. So, I am just connecting this to some of the concepts you may be already familiar with, but nevertheless coming back to the Michelson. So, we defined things such that, okay, this distance we called as d1, this we called as d2, and we were looking at delta phi, which we said is 2 pi over lambda 2 multiplied by d2 minus d1. This we said has to be equal to 2 pi m for constructive interference criteria, and then we said, okay, in this we can essentially cancel 2 pi and then come up with this expression that we were seeing previously, which is d2 minus d1 equals to m lambda over 2. Okay. So, suppose I am looking at this, I move one of these mirrors. Okay. So, initially let us say I have this condition that d2 equals to d1, right, and then I start moving one of these mirrors, right. So, I am plotting d2 and I am plotting the intensity of light that I get over here, and what do you see if I start from, let us say, d1, right, what do I get to see? So, at that point it is maximum, right, because the phase difference is 0, and then it is going to go through this, and then it is going to go through a maxima, minima, maxima, minima, and so on, right. So, of course, you can define the next maxima to be happening at d1 plus lambda over 2, the minima would correspond to d1 plus lambda over 4, and so on. But the key point here is that we are saying that the intensity is going to be constant, okay, irrespective of whatever the value of d2 is, okay. And we will now question this particular assumption, okay. Is this constant for whatever d2, okay. Now, to do that we will have to examine what we are observing a little more closely. Okay. So, you are observing the beating of u1 of t with u2 of t, right. And in fact, as we saw, we are observing the complex u1 and u2 are complex quantities. So, the beating would correspond to u1 conjugate u2 and then u2 conjugate u1, right. So, if we look at this and then we look closely at what u2 of t means. What does u2 of t in this case? Is it different from u1? Yes, it is different. It is going through a different arm and then the different distance is different, but otherwise is it different? Not really, it came from the same source. So, I can basically write this as u1 star of t and then u1 of t plus tau, and of course, when we are making a measurement, we are not making a instantaneous measurement, right. If you are to make the instantaneous measurement, the light frequency at 1 micron, it corresponds to 10 power 14 hertz. Okay. So, when you talk about the time scales, the period with which this oscillation happens, that period corresponds to some femtoseconds. So, we are not doing any measurement in femtoseconds. So, what we are doing in general is a time averaged measurement. So, what we are observing is this quantity. Now, does that tell you something? The structure of this, does that remind you of something? That is the correlation. In this case, it is the same source, so it is basically autocorrelation function. So, through the Mach-Zehnder, what you are really observing is the autocorrelation function. Okay. Now, if you have a plane wave, a plane monochromatic wave, okay. So, that is what we are assuming, it is a plane monochromatic wave. If you have a plane monochromatic wave incident on it, then you can basically say it is going to have that light wave is going to have a certain amplitude, let us say u naught, right, and then as far as the phase is concerned, you have e power j omega naught t. If it's a monochromatic source, then you can write it as e power j omega naught t, and then this one is going to be u naught e power j omega naught t plus tau, right. And if you take a conjugate of u1, so that corresponds to minus over here. So, the result that when what you get out of there is basically u naught square e power j omega tau, right. Now, this autocorrelation function, let us say we represent this as g of tau, okay. You can now define another quantity, let us say this is let us call this the degree of coherence. So, the degree of coherence is small g of tau, and that is nothing but this capital G of tau divided by this u conjugate of t multiplied by u of t. So, this is nothing but the total intensity in that wave. So, what we are doing is in defining the degree of coherence, we are basically taking this g of t, which we call as the temporal coherence function, and we are normalizing that. We are normalizing that with the intensity. So, g of t is now a normalized coherence representation in what we call as the degree of coherence. And if you look at the the magnitude of that degree of coherence, g of tau, magnitude of that magnitude, what does that correspond to for a monochromatic wave? So, what will be the magnitude of g of tau for a monochromatic wave? That will be the magnitude. So, you have a u naught square, but u naught square is going to get cancelled here, the denominator. So, what you will have here is just magnitude of e power j omega tau, which is 1, right. So, for a monochromatic wave, magnitude of g of tau will be equal to 1, okay. And you can also define on the other end of this spectrum, where we say if you have a totally uncorrelated sort of source, then that is going to be g of tau equal to 0. So, g of tau is essentially something that is going to take values of less than or equal to 1, greater than or equal to 0, okay. So, we say 1 corresponds to a perfectly coherent source, in this case what you call as a monochromatic source, and g of tau equals 0 corresponds to a perfectly incoherent source, okay. So, when we look at what this monochromatic wave represents, let's look at this in time, right. In time, this monochromatic wave is going to be a nice periodic function, right. So, this is with respect to time. So, that would imply, let me call that as nu. In frequency, how would that be? A delta function, right, a delta function with nu naught as the frequency, right. Now, this is a perfect monochromatic source, but that would be an ideal source, okay. But when you look at non-ideal sources or practical sources, what you see in them is something like this. As a function of time, essentially it is going to have, if you take a Fourier transform, if you look at the power spectral density, that power spectral density is going to look something like this. It has a center frequency nu naught, but a width that corresponds to delta nu. When we have a mixture of multiple frequencies, you do not have a perfect periodic sort of pattern, you have nondescript pattern as far as the temporal behavior is concerned. The key point here is that if you look at the autocorrelation of something like this. So, what we are plotting here is S of nu, which is the power spectral density. So, we are plotting S of nu over here as well. Okay. So, if you look at, if you know the power spectral density of a source, you have an expression or we have a theorem which is called Wiener-Khinchin theorem. Have you heard of the Wiener-Khinchin theorem? You've done something in communications or signal processing, you might have come across that. What the Wiener-Khinchin theorem says is that the power spectral density and the autocorrelation function, they have a connection between them. Essentially both of these are Fourier transform pairs. So, S of nu can be written as minus infinity to plus infinity g of tau exponential of minus j 2 pi mu tau d tau. So, what you see is that both these the power spectral density and the autocorrelation function are connected with each other. So, knowing the autocorrelation function, you can compute the power spectral density, or conversely knowing the power spectral density, you can compute the autocorrelation function. So, if you do this inverse Fourier transform, so what you will find is g of tau over here as a function of tau, and you will find that the autocorrelation function is something like this. And do not worry about the shape of this, because the specific shape of this depends on the specific shape of the power spectral density, right. But when we look at with respect to the delay that we are imposing, you would essentially see that this coherence function means that it will actually be maximum when the delay is 0, but it starts falling down once you start having a delay. So, why is this relevant? Now, you go back and look at what we were discussing over here. We were essentially saying that as you move one of the mirrors, we are trying to figure out how the response will be, okay. And for a monochromatic wave, the response will be like this, that it will go to the maximum to the same point as you move d2 to infinity, right. That is what it says here. But for non-ideal sources which are polychromatic in nature, when you have a frequency spread, that coherence, the temporal coherence is actually limits your interference, okay. So, it limits your interference such that instead of this, you may have, if this is my average point, then the envelope of this would essentially go like this. So, you will not reach the maxima completely, you will not reach the minima completely, and at some point it will just be the as if the two beams are not interfering at all. So, what we are essentially doing, maybe I did not make this explicit, is we are looking at the autocorrelation between two of these wave fronts, okay. So, as we move the distance d2, you are like looking at farther and farther out in space or in time, Okay. So, these two are reversible. So, you can go back in time or in space, and you take different components of the of waves from different wave fronts from the same source, and you are looking at how well they are correlated, right. And what we are saying is, if it is a polychromatic source, that correlation holds good only for a certain time or a certain distance. Okay. So, and beyond that it will start reducing in terms of the overall contrast between the maxima and minima, and that reduction is essentially defined by the envelope of this autocorrelation function. So, effectively what we are saying is, when we are looking at the Mach-Zehnder interferometer output, let us say we are looking at this as a function of tau, and let us plot this as I over 2 times I naught. So, 2 times I naught corresponds to the I naught would be the intensity in each of the arms. So, okay. So, it can reach a maximum of 2 times I naught. So, when we look at this, what we will find is that envelope will follow so this takes a value of 2 over here and 1 and 0 over here, and so that takes an envelope like this, and inside this, if we look at the specific interference pattern, that interference pattern would be like something like this. Okay. So, do you understand? So, this is, so as we are moving D2, we do not retain the same contrast. Okay. As we go to longer and longer values of D2, longer path length differences, you do not have the same contrast, and this where it goes to half that contrast is what you call as the coherence time. Okay, the width over which you go to half the contrast is the coherence time. Okay, and what we are also saying here is that the coherence time is inversely proportional to the spectral width. Okay. So, that proportionality constant actually depends on whether the shape of the power spectral density. Okay. So, it could be a fraction, but tau c can be approximately given as 1 over delta nu. So, larger the spectral width of your source, smaller will be tau c, and in terms of spatial quantities, you can say this is coherence time, and in terms of spatial quantities, you can define what you can call as longitudinal coherence length LC. LC is going to be c times tau c, where c is the velocity of light in vacuum, right, or free space. So, in terms of length, it is just directly proportional to tau c. So, I will just take a minute to give you some examples of different sources and the corresponding coherence time and the coherence length. So, let us look at sunlight, which is from 0.4 to 0.7 micron wavelength. You have a semiconductor LED, let us say at lambda naught of 1 micron, and delta lambda typically corresponds to 50 nanometers. And let us say you also consider a laser diode, the same wavelength lambda naught 1 micron, but delta lambda in this case would be 1 nanometer. And we also consider a helium neon laser, which is lambda naught of 0.633 nanometer, and delta lambda which is in the order of picometers. So, we consider all of this in terms of let us look at delta nu in hertz, and let us look at coherence time and the coherence length. Okay. So, this would correspond to a very wide spectrum. So, this is 3.75 into 10 power 14, and the corresponding coherence time is 2.67 femtoseconds, and coherence length would be 800 nanometers. Okay. Whereas a semiconductor LED, which is a much lesser in spectral width, that would correspond to 1.5 into 10 power 13 hertz, correspond to 67 femtoseconds, and that will correspond to a coherence length of 20 microns. Okay. So, what we are saying is it's sunlight D2, you have perfect condition equal to D1, you get to see some fringes, right, you get to see some maxima and minima, but the moment you move even fraction of a micron, you lose all your fringes. Okay, you don't have any. So, it's very hard to make interference fringes with the sunlight. Okay, whereas with a laser diode, it's 3 into 10 power 11, which corresponds to 3.3 picoseconds, and here the coherence length is in the order of a millimeter. And finally, this is something that we can, it's 1 megahertz is the helium neon laser line width, which will correspond to 1 microsecond coherence time, and 300 meters. Even if you take D2 to 300 meters, you still have some visibility, you can still see some 50% visibility. Sorry? 633, oh, thank you. So, yeah, this should be 0.633 microns. Thanks for pointing out. Okay, so let me stop at this point. So, what we have just now started is quantifying the coherence of light, and we say based on the fact that it's typically a non-monochromatic source that we are dealing with in practice, the coherence or the range of delays over which we can see interference between these two constituent waves is limited. Okay. So, let me stop at that point, and of course, what we are saying is that that coherence time or the coherence length is inversely proportional to the width of the source spectrum. Okay. So, let us stop at this point and we will continue from this point tomorrow. Thank you.